Right, we are back with some quick math. Like, subscribe, share the videos with anyone that is doing math or technical math, grade 11, grade 12. It will definitely be beneficial unto them. Right, let's get into the theorem. So we're still busy with Euclidean geometry, and we have um, our bow tie theorem. I think this is theorem number 4. I'm just going to move some things around here. I just wanted to see how it works. Then I will explain some concepts, and then I'll do the proof as well. For you, this is not a proof that you will need to be able to do by yourself. But it will be beneficial for us to look at it. So let's do that quickly. So if I move these points, I notice that wherever this goes on this side of that circle, it always stays the same as the other angle, right? So if I put this, it's always going to stay the same. If I move this one, my two angles are still the same, and wherever I take these, it is still going to stay the same. Right, so this theorem over here, we call it our bow tie theorem. Something I want you to notice is that all 4 points that I am moving around, or all 4 points that I have, are on the circumference of the circle. Now, one of the common mistakes is it looks similar to theorem 2. However, theorem 2, one of your 4 points are on the center and the other three are on the circumference. For this one, all 4 points are on your circumference, right? That's the outside of your triangle. Great. So over here, we'll do the proof up there, but for now let's just draw some things over here. So we had these 2 points, right? So you had a point there and you had a point there, and then I was moving around those other 2 points. So I'm first gonna draw in a dotted line over here. So here's a dotted line, right? And we're gonna name these points. This is gonna be point A, and this is gonna be point B. So what we saw in that previous image, the one that I was moving around so nicely, A and B subtended a point, right? So we spoke about in one of the previous video what subtended mean. It meant that A extends to a certain point and B extends to that same point. So A and B subtend, and let's call this point C. So chord AB, they go and form this angle C. AB, they can also maybe subtend another point. So AB, they go and form together, together they go, and they form another point, and we can maybe call that point D. That's going to be the same thing. AB can go wherever it wants to go. It can go subtend another point there, call it E, whatever, and it will also be the same thing. So C, D, E are all the same thing because all of them came from this AB that subtended different angles, right? Notice something that that all the angles that we subtended, all the angles C, D, E were all on that side, right, of our chord AB. Right, I didn't take anything on the other side of our chord. Okay, great. So that's how the theorem works. Okay, let's maybe get rid of some things over here. Let's get rid of all of this. So that kind of looks like a bow tie, right? The chord A, B, which is the dotted line that we put in, we normally don't see it. So this is normally what you see, right? But I want you to understand that there is a chord here, and that chord is the one that goes to subtend an angle, and wherever that angle is created, it is the same thing. Great. So let's work on the proof. Okay, let's clear this so that we have some space for our proof. Okay, so again, we mentioned that all of our points are on the circumference of the circle. Okay, so let's name them. This can be A, this is going to be B, this is going to be C, this is going to be D. All of the points on circumference. Something I want you to notice is that we are not given the center of the circle. Right, so I'm going to draw in the center over there, and I'm going to call the center coordinate O. It was not there, so it's part of my construction. Construction is something that I'm drawing in. Okay, and then I'm going to draw in, let's do my construction in a dotted line here. Okay, I'm going to draw in that one, and I'm going to draw in this construction over there. Okay, so those are some things that I drew in myself. They weren't in the original question. Okay, so the next thing that I want you to see is because of my construction, there are arrowheads that are created. So here is an arrowhead, right? And now if we remember theorem 2, we said that was the arrowhead theorem. How did that one work? That one said angle at center is double the angle at circumference, right? So let's write that down. We'll say that angle O is equal to 2 angle C, right? The one in the middle is double the one on the outside. How do we know this? What's your reason for this? Angle at center, angle at center. Let's just write this out nicely. Angle at center is twice, 2 times angle at circumference. Right, so see, we're not going to write out the whole word, just circumference. So that's angle at center is twice the angle at circumference. Then I want us to, let's maybe use a different color here with our highlighter. We can go back at this circle and we can see that there's another arrowhead formed. The other arrowhead formed is over there. All right, and again, what does the arrowhead theorem tell us? The angle at the center, so it's again this O that we see over there is equal to double angle D. All right, let's write that down. So angle O is equal to 2 times angle D. Right, and again, the same reason, angle at center equals 2 times angle at circumference. All right. Okay. So what we are saying is that we are saying that let's put it in some random color. Let's make it green. We are saying that this O is double C, but also that this O is double D. All right. So basically, we are saying that this is O, both of them are O. So if both of them are O, then clearly they need to equal to each other. So then 2C must equal to 2D, right? And we'll get rid of the 2's on both sides. So therefore C is equal to angle D. Okay, great. And the reason we're going to write, so when we write this, okay, the reason we're going to use is we're going to use angles in the same segment. Okay, let me write that again. Angles in the same segment. That's more legible. Okay, angles in the same segment. The bow tie theorem, the reason you put in brackets is angles in the same segment. Okay, so what is a segment? So let's maybe decide what or define the segment. Maybe I'll make a video at some point about the definitions, just to help us, right? But let's get a circle here quickly. Right, so there is a circle, and we're going to draw on the circle. So we had not coordinates, we had points A and we had points B. Right, if I draw in the chord, right, that we said over there, the chord AB, then there's 2 segments that are created. The one that's on this side and the one that's on this side. There's 2 segments created. So what I want you to do now, kind of ignore, I don't think we can erase on this app. Ignore this part that I'm putting in gray over here. Ignore that part of our circle, and now you only have the upper or the major segment, right? You only have this bigger part here on top. Okay, so what the theorem that we have says is that if AB subtends any angle on this side, so wherever AB goes are through 3 random angles there, wherever AB is going to go, they will form the same angle, right? Angles in the same segment. Previously, and I think some of our textbooks will still say AB subtends equal angles as a reason, but that reason is no longer valid. Right? There's a document that I've sent to most of my learners, and that document tells us what's the acceptable reasons. The acceptable reason for this theorem: angles in the same segment. Make sure you use that. Okay, hopefully you caught all of that.